So the guy who did this, first did this, was Reynolds. And he basically knows that if he put a dye in that flow, in a pipe flow, and he watched the dye, at very small velocity, the dye basically become laminar like this, and then once he increase the velocity, it basically, the dye start going up and down. So he realized that the fluid carrying this dye basically go up and down, up and down. Together with the uniform or the average velocity is basically to the right. That's an average, everything is going from this side of the pipe to the other. But on top of that, there are basically all those fluctuation, right? So that's turbulent flow. And he basically tried to measure when would this really happen? And so he came up with that Reynolds number, right? And so we now realize that once you hit that critical Reynolds number, that's when the balance between the viscous force that's trying to damp all those fluctuation and the inertia force that's trying to initiate them, and mathematically all those fluctuations come from the nonlinear term in the equation, the u partial x and the u partial y, sorry, the v partial u partial y, and the w partial u partial z. That's in the x momentum equation, and then the other three term in the y and z momentum equation. Those non-linear term mathematically is the one that's generating all those fluctuation, right? And so those fluctuation basically are always under control when the Reynolds number is small, when the viscous force is very strong, when the flow is very viscous. Then those things cannot get initiated or cannot be basically sustain themselves. But once you lower the resistance to their creation, then they basically start becoming really strong, and you cannot damp them, right? So for a flow, for example, over a flat plate, we know that this limit is reached when the Reynolds number hit 5 × 10⁵, right? And here's a picture of what's really happening. You can actually see that basically all those kind of vorticity start being created at the wall, right? There are those kind of like small circulation that's basically created at the wall. And it was, people speculated about this, and I remember when I was a student, I couldn't really believe my professor when he was talking about it. But then when I became a professor, and now people actually managed to see the flow near the wall, in just like few years ago, 3 or 4 years ago, people managed to actually see this vorticity really forming at the wall. And so you can see this roll of circulation basically being created because, again, the velocity gradient near the wall, the fact that this fluid particle is trapped from the wall and the guy on top of him is rolling faster than him. So he tends to rotate, right? And so that sheet basically get kind of a lifting force that pull him up, and it formed this horseshoe vortex. It's like a vortex, a filament of rotation that's basically like a horseshoe. And then it basically just break into the flow, and you basically had all those chaos being created. So that basically, that mechanism, people then thought about, well, then maybe we can destroy those structures before they basically establish themselves. If we can cover the submarine surface or the aeroplane wing with all those like MEMS devices, very small tiny objects that can have a shear sensor, shear stress sensor that can feel one of those things forming, and then hit it with a jet, a tiny jet that basically just break it apart, then we can actually maintain laminar flow over a very long surface, right? So there are all ways of basically boundary layer control, how we can maintain it laminar and don't basically let those structures basically form and hold themselves, all right? But anyway, they do, and once they establish themselves, because of that strong mixing, you will see that a turbulent boundary layer have much bigger height than a laminar boundary layer. So a laminar boundary layer will be very short, but a turbulent boundary layer will be really huge. And on top of that, the fact that it's really big, really high, also near the wall, it brings a lot of velocity. Look at the laminar boundary layer. The velocity near the wall is almost zero, right? But a turbulent boundary layer bring very high velocity. to the extent that you would look as if there is actually velocity at the wall, but no, there's still a zero. But he's basically trying to show you that it feels as if the turbulent boundary layer bring a very high velocity all the way down to the wall. That's how strong the velocity is at the wall, right, for a turbulent flow. So that, of course, creates huge drag, right? So it's, when you look to it, it's as if the turbulent flow basically has increased the connection between the layer and each other. He basically made everything aware of everyone else, right? So what property that actually do this for a flow without turbulence? For a laminar flow, a flow that's very well connected, the top layer know exactly what's happening down there, is very viscous flow, right? A flow with very high viscosity. So the easiest way to model turbulent flow is to increase the viscosity. And so I remember when I was a student, I couldn't believe what the professor was saying. What do you mean? So to become turbulent, fully turbulent, you make the Reynolds number really, really small by increasing the viscosity, right? So it doesn't really make sense, but that's what happened to the velocity profile. It's as if suddenly the viscosity is really high and the flow is just moving as one block, kind of. He really know everything going on at the bottom and the top. Okay? All right. So again, the sad news is that once we go from laminar to turbulent, you basically switch to a higher drag. All right? That's what we don't like about it. You increase the drag, and therefore you increase you have to increase the thrust that have to overcome that drag. All right? And so when people first start measuring that turbulent flow, and we'll talk about measuring mechanism later today, they basically put some kind of a PT tube, a very sensitive PT tube, or something called hot wire. It's different from the oil wire, but hot wire, they put it in the flow and they start measuring the velocity. All right, and they measure the velocity they have to measure to something that's have very quick response, right? So basically, because it's really unsteady, so on top of the average velocity, you get basically all those fluctuations. And one big thing that they noticed was that for some point you basically get nothing. Okay, that was a really big thing when I was a graduate student. Okay, some 20 years ago. So they basically will see like nothing. It's like the turbine just died on them, and then fluctuation again, and then and they call this intermittency. Like the flow is intermittent. It's like he's on-off switch, and so they wonder what's going on. And so with the advancement of laser diagnostics and imaging, they figured out there is actually large-scale structure. There are all those rolling vortices that if you have your wire or the device that you are measuring with sitting over here, and those guys are passing by, you will come in a place where you don't measure anything. And then one of those guys will roll over and you'll start measuring, tack, 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 tack. And then silent, and then coming again. So it turned out that every single flow has its own large-scale structures. Okay? So if I basically introduce a jet in ambient air, there are certain large-scale structure or large eddy. Okay? If I have two shear layer, for example, high flow coming and lower flow, exit of a duct or something. You are sending the duct into a room. That's also another kind of large-scale structure. They will actually look like this. All right. So it turned out that there is this large-scale vortices or large-scale structure, but on top of them, there are also the tiny, small one. So the turbulent flow is basically consisting of a cascade of sizes. Okay, there are the big one, and so those big ones have the scale of, say, the volcano exit, or the pipe diameter, or the duct. This is how large it is. So the large scale structure, those are dominated by the geometry that we are dealing with. And then there are all those tiny guys, and those tiny guys increase with the increase in the Reynolds number. So as the Reynolds number of the flow increase higher and higher, those small tiny things get smaller and smaller. So why? Because it turned out that the small vortices are very expensive from energy point of view. It's very hard to sustain them. Why? For a free quiz, why do you think it's very hard to keep them rolling? Those small tiny ones. Say that again. I can't hear. You have to raise your voice.
The area, because the area it's occurring in, you have to have more pressure, more energy to keep it in that area. But
It's not the pressure.
collisions?
No. It's the homework that we did just a few minutes ago. Huh?
Something to do with the viscosity, maybe, where it's detaching itself from the streamline flow.
It has to do with the gap width. The 0.3 millimeter. The gap, the oil gap, we solved the problem over. When that distance is so small, when the size is just very small, the shear rate, partial U, partial Y, is very big. And therefore, the shear stress that will be generated out of it will be really huge. The viscosity will kill it, basically. So to be able, the resistance is really huge for something with such a high shear rate. Okay, if the gradient is really high, that means the shear stress is really high. That means it takes a lot of energy to sustain those guys and keep them rolling. So if you turn off the power that sustain that flow, if this was like a flow not from a volcano but from a fan, and if I turn down the fan, the first one that will die are the small one. Okay, and the big one will be basically keep rolling a little bit more. Okay, if you put some kind of die in a cup and rotate it with your hand, and you pull your hand out, the first one that will die are the small scale. Okay, those are very expensive to sustain. All right, and so they made this kind of energy cascade model. They basically realized that, well, then the flow get his energy at the large scale, and then it being passed to the smaller one and smaller one and smaller one. Okay, and the smallest one, that how small it will get, is basically controlled by the Reynolds number, how high the Reynolds number is. All right, so here are more cool picture of basically how this basically get initiated. The large scale structures start form first, and then smaller one start forming, getting energy out of them. All right, and so now what we're interested in now is how we can simulate, how we can get the flow described by equation to solve something like this. So what is the equation that will simulate something like this, so that we don't have to do the experiment, but we rather do it on the computer? The good news is there's no more equation. You are done with the equation. You already had all the fluid mechanics equation you need. It is the Navier-Stokes equation. So the Navier-Stokes equation that you use to solve parallel flow, laminar flow, it's still the equation that will be used for turbulent flow. What's the problem then? Okay, I mean, those partial differential equations, we discretize them like we learned in 3013, or that almost similar to what we had in heat transfer too. You know, when they had this mesh and they write the finite difference and they turn the differential equation to algebraic equation and send it to a solver. What's the difficulty then? Can anyone expect what's the difficulty? I want to simulate that volcano flow with the Navier-Stokes equation. What's my problem?
You have no boundaries?
No, we have. I mean, here is the velocity. You can imagine there is a boundary over here, okay, and the boundary here is velocity equals 0, or the pressure is ambient, and here this is basically kind of exit flow.
Measuring your initial velocities in the different directions?
We can assume it. It's not a big deal. We can go to try and error. That's not the big deal. The big deal. You are going somewhere. You are going somewhere with this answer. What do you mean? Why do you want it to be symmetric?
Because
You want to reduce the size of computation, right? You are saying let's not do the whole thing. Let's only do half of it. So that's okay. You can get a bigger computer, but this is the right direction. The problem with Navier-Stokes equation is solving something like this is look at the size of those small tiny guys. They get smaller and smaller as the Newton's number get higher and higher. So what does this mean? It means that in order to simulate something like this, I will never capture this eddy if my grid is this big, right? I need a grid smaller than the smallest one of them, right? The smallest eddy if I would like to simulate students fighting in a classroom, okay, kicking each other, and I need to have a grid so that I can see you. If my grid is basically like 4 by 4, you will not show up on that grid. At least, I need 2 points across cis so that I can see cis as at least a pixel. 2 pixel by 2 pixel, so that at least he's like a square, and then I can see the square hitting Roger's square and then Roger's square bouncing back. I mean, at least 2 by 2. So imagine if you are gonna fit grid points in the smallest eddy of those guys, then it turned out that it's a disaster. It turned out that it's a lot of data points. We're talking about billions of data points in the grid. However, they have supercomputers, right? We lost our biggest computer title to China now, but still we have the second largest computer in the world. So we can fit a tiny problem, not flow over an airplane, but a tiny problem, and solve it like this. When we do this is called direct numerical simulation. So in the question about this, I'm not going to give you the question to solve it, but I can give you multiple choice, for example. Okay, I will tell you what is direct numerical simulation. DNS. So direct numerical simulation is basically using the Navier-Stokes equation to solve turbulent flow by basically having a very fine grid. The grid should be smallest than the smallest thing that ever happened. Not just in X, Y, and Z, but also not X, Y, and Z, but also need to be small enough in the time direction. So because those guys are unsteady, you need also the time step to be really tiny so that you can basically track every single movement they have. All right? So it turned out that basically it's really hard to do this for a practical problem. For a really large problem, you don't have enough. Really, you don't have enough. Right? And I remember my PhD advisors telling me I will die before he will die. Before he did pass away, 2005. He said I will pass away before they solve this over practical problem. And he was right. Probably I also will pass away before they solve this for a really large scale problem. Right? But you can solve it for decent problem now. Right? So what is the next step? The next level is basically LES, large eddy simulation. And so that name cannot be better chosen than this. Large eddy simulation basically saying that, let's not make the grid solve the tiniest one. The tiniest one, we can skip them. Why? Although there's a lot of things happening at that small scale, that's where all the energy is being lost into viscosity. But they can basically model that effect. They can basically say, at that Newton's number, we know that the smallest one will be, we measured them, we know that they will be that size, and they will be wasting continuously, 15 watt of energy. We know what will happen to them. So let's basically just make sure that the grid is small enough to get the large eddy. The eddy that we don't really know how they behave. But the smallest one, we will basically model their effect. Okay? So this is called large eddy simulation. So both those are not really popular with industry. If you once you graduate and you work with companies, they don't want to do direct numerical simulation and go to the supercomputer, and they don't want to do large scale simulation and run for weeks too either. They want the run to be finished tomorrow. You come back tomorrow and you tell them, you know, how quickly the air should be in that boiler, or how large the velocity should be inside the burner. So what do? What they do is something called the K epsilon model, right? So the K epsilon model, that's basically what's popular with industry, right? That's how they model this is how they model turbulent flow. Okay, so how do they do this? Well, they basically start by saying that real action, you know, that velocity fluctuation with time, we can split it into two components. One that's the average, average, and one that is the fluctuation. All right? So the velocity everywhere in our burner or in our heat exchanger or out of our radiator fan, yes, it's fluctuating like this. We know that's what turbulent flow is. But on top of that, or not on top of, but under that fluctuation, there is an average. And if you give us the average, we are happy because you are going to get it tomorrow for us rather than waiting for weeks to tell us. And even if you give us those fluctuations, we don't know what to do with them. We just know we want to know what's the average velocity at everywhere inside this furnace. All right? So they basically, every velocity, they split it into average and fluctuation. Average and fluctuation. U and V and W, they are all split into average and fluctuation. And then they put them inside the Navier-Stokes equation. All right? So the Navier-Stokes equation, that was basically partial U partial T. That first term, remember, there was rho partial U partial T. That U become U average plus U fluctuation. And partial T, the partial T basically can go into, if I have partial T A plus B, I can say it's equal to partial A partial T plus partial B partial T, right? And then I average the whole equation. And so when you average the whole equation, the average of the fluctuation is 0. By definition, they don't have an average. The average of the mean is the value of the mean, but the average of the fluctuation is the fluctuation. So when they do this, they get rid of all those fluctuations, and the equation become an equation of average. Excellent, right? Because they want only solve for the average. They don't want the fluctuation anyway. Except for, so everything is, I mean, this is the average. It looks exactly like the Navier-Stokes equation, right? Except for new terms that show up because of this averaging process. And it's U, this is U fluctuation in the direction of I multiplied by U fluctuation in the direction of Z. This is as if he's basically telling you U prime V prime or U prime W prime. And you are trying to average this. Okay? So I know that U prime average is 0. By definition, U prime average is 0. But U prime V prime average is not 0. Okay? It's not 0. I have no idea when they hit when you multiply them by each other, do they get a spike plus and then very small minus, so that when I average them at the end, I had more plus than the minus, and therefore it's not going to be 0. I know that if an average U prime and it's completely random like this, I will get 0. But if I multiply this by this, and then the total is basically, well, then this guy, when you average, is not 0. It's something. So what's the solution then? What's the solution? You have almost an Navier-Stokes equation, except for those new terms that showed up. See, this is Navier-Stokes equation. This is Navier-Stokes equation. This is Navier-Stokes equation. Unsteady term, the convective term, basically the body force, and the viscous force. Those are okay, right? But those new ones are not okay. So we have two approach. Okay? One of them is called the Reynolds stress transport equation. Okay? This is first, here's the slide when I'm telling you that it's U prime, V prime. This is the fluctuation. For it to be zero, you will have to have basically totally, they are not independent of each other. They have to be completely independent of each other. U can be anything, V can be anything, right? And that, if this happens, this is called isotropic turbulence. This is turbulence that doesn't have X and Y and Z. This is basically turbulence that have no direction. This exists only in our textbook. Or in really well-designed experiments when they put like fans everywhere and they direct all those fans to the middle of the box and measure what happened in the middle of the box. Why did they do this? Because it's scientifically interesting to see a turbulence that doesn't know where is X, Y, and Z. But most flow will know X, Y, and Z, right? So maybe the flow is not isotropic. Maybe the flow is anisotropic. He has a direction. And U prime, V prime is not zero. But it have a value. So the first approach is basically to say, well, if those guys are not zero, U prime, V prime, and V prime, W prime, and U prime, W prime, all those guys does not have a zero, and still I need them for this equation. I can solve the Navier-Stokes equation if you take all those unknown. I cannot afford to have any more unknown. The three momentum equation in X, Y, and Z are enough to solve for the average U, the average V, and the average W. So I cannot afford to have U prime, V prime in my equation. This needs to be given to me. Right? So they do it by basically saying, you know what, let's, we will get you U and V and W by basically saying that they represent some kind of how much energy is lost or how much energy is within that turbulent flow, right? So let's pull them into something called K. So K is the mean kinetic energy of those turbulent velocity fluctuations. So it's U squared plus V squared plus W squared. All right? And there is something called epsilon, which is how quickly does this turbulence die. So maybe it dies because of the dissipation of the viscosity. The viscosity basically kind of kill it. It doesn't want to have the flow to keep fluctuating like this. So this, the equation that describes those two guys, is called the K epsilon model. And that is the most popular model that industry use. Okay, so you go to anyone making furnaces or making heat exchanger, and they would like to simulate that turbulent flow. They will have the three momentum equation, U, V, and W, and next to them, you are solving for K and epsilon. Okay, the code or the software that's solving this will solve for K and epsilon. And so they will write an equation for K and they will write an equation for epsilon. Okay, and it's interesting how this equation is being written because it's not really physical. It's kind of a mathematical equation. You are trying to write an equation that describes what happened to those three fluctuations. All right? And so solving this K and epsilon equation will supply those guys. Okay? If we didn't finish those guys, if we don't have value for those guys, we have something called the closure problem in fluid mechanics. And so that closure problem is when we write the equation for the average, we get the fluctuation. And if you try to write an equation for the fluctuation, you could say, well, I can actually drive an equation that control U prime, an equation that will control V prime, an equation that will control or describe W prime, equation for each one of them. Those equations that describe U prime, VW, and W prime, and U prime, V prime, and W prime will actually have the second order fluctuation. Okay? So the problem never finish. Every equation have the higher order fluctuation. So at one point, people decide we have to close this. We have to close this problem by coming with kind of a model at the end. You basically say, I know this number. I think it's 5. From experiments, from theory, but you close the problem at a certain level. Right? You cannot just basically keep driving higher and higher order equation, otherwise it becomes really huge. And mathematically it's very tough to integrate. Alright? So the model basically come at the end, this closure problem come at the end, basically realizing that at the smallest tiny level, the smallest that will exist will be something called the Kolmogorov length scale. So that is kind of the tiniest eddy that would exist. So those guys, the tiniest one in the flow, those are called basically the one that's really isotropic. Those are called isotropic turbulence. At such small scale, they don't remember anymore where is X, Y, and Z. They don't know where is the mean flow is, and the smallest tiny one. And therefore, all their property are just function of the viscosity of the fluid, nu, and how quickly the turbulence is dying, epsilon. And so they can come up with their size. They can come up their size basically based on totally dimension analysis. Okay, so the guy actually came up with this idea in 1941, and so far it's the most popular idea when it comes to closing the turbulent flow, rather than doing DNS on supercomputer or large eddy simulation on a little bit bigger computer. If you want to close the turbulence and you don't want to drive bigger and bigger equation, you basically come up with a model for what happened to those small eddies using Kolmogorov length scale and velocity scale. All right? Those smallest eddies will have a unit number of 1. That's how viscous they are. I mean, they are swimming in basically in honey. Okay? Mainly dominated by viscous effect. All right? So here is, so by UI, UJ, I basically am saying like U, V, or VW, the two components. All right? So once you solve for K, once you have your K in your hand by solving that K equation, then you can have all those fluctuations by this model. So it's K, delta, what's delta? Delta Ij. That's the Dirac delta function. So as if I and j is not equal to each other, it's 0, and if I equal j, then it's 1. So basically, ux, uy will make this 0. Anyway, that model, basically, those are the average velocity. Those are average, which we know from solving the Navier-Stokes equation. And this is basically the K that we solved. All right? And so here is the Navier-Stokes equation for turbulent flow. Right? And so this is the one that basically you would be solving, and you will get the average value, and K, you will come up with that K value from solving the K equation. Right? So that is the K epsilon model. So one hard thing about this is when you are solving the Navier-Stokes equation in a grid, you apply the boundary condition, right? You say, well, I have the inlet in the duct. Here is the velocity at the inlet. I have the outlet, pressure outlet. But when you introduce two more equations, K and epsilon, now you have to worry about the boundary condition of the K and epsilon equation. You also have to know what is the level of turbulence coming into the grid or into the model that we are trying to simulate. What's the boundary condition of the K? And the same thing for epsilon. And on top of that, one really big problem is the equation will have, the equation will have tons of constants, a lot of constants. Just like this, a viscosity, the eddy viscosity, that you have to worry about, well, how are you going to model this? This is kind of the viscosity of the turbulent flow. It's not the viscosity of the fluid. It's the viscosity of the flow. So the difficulty with turbulent modeling is those constants like this, or the constant that will show up in the K and epsilon equation, they are not always the same as long as you have water. No, if water is going into a step, it's different from water going into a jet, it's different from a water going into a flat plate. Each configuration, each geometry has its own set of constants. So what you need to remember when your boss is telling you, well, can you run this model? This is We did this for turbulent flow over a pipe. We are just doing it for our rectangular duct. Tell us the flow rate. Just try it again with this new geometry. So you enter the new geometry, but what you need to worry about is the constant that did run for pipe may be different when you are simulating a duct. All right? So the K equation would be like this, something like this, right? Look at that. It's I could write this equation actually myself from scratch. It's kind of unsteady term. What's that? Can anyone guess what's that? U partial K partial X. That must be convective term, right? Unsteady term, convective term, and then a diffusion term. Okay, just like velocity was diffusing, also K is diffusing, dissipation term, and source term, gain from mean flow. So they are modeling it exactly like they modeled the momentum equation. All right? And so here is the K epsilon. This is when you have equation for K and equation for epsilon. All right? So again, unsteady term for K and epsilon, convective term, diffusion term, dissipation term, and a source term. Just like the pressure gradient used to generate velocity, well, here is the mean flow generating fluctuation. You're generating turbulence. All right? And all those C and all those epsilon, all those constants, C mu and C epsilon, and all those guys, see, look at that. All those guys are numbered that they tuned in order to make this equation really simulate very well pipe flow. Okay, but then when they move to shear flow or they move to different kind of flow, separated flow, then they have to retune those numbers to fit the experiments, right? So that's the difficulty, that it's basically lack of generality. It's not the same numbers everywhere, all right? Those are the two equations, the K and epsilon, that they add them to the Navier-Stokes equation, the three momentum equation. And the 5 of them are now a set that simulate turbulent flow. And we wouldn't have needed those guys, the K and epsilon, if our grid was fine enough so that the Navier-Stokes equation by itself can solve the smallest one, the smallest eddy. We are into this trouble because our computer cannot make the mesh fine enough to get the smallest guy. Okay? But when I was a graduate student, I took one math course, the whole course. We spent one semester to prove that Navier-Stokes equation is the equation for turbulent flow. And I can tell you at the end of the course, yes, it is. So the Navier-Stokes equation, and not only that, but we proved that it has a unique solution. Right? But we cannot get it, but there is a unique solution. We cannot get it because it's very sensitive to the initial condition. The moment you change a little bit of the initial condition, the solution go this way or that way. It's basically the reason why the forecast at the 10th day never works. Not because they don't have the equation, they have the equation. But when they start the initial condition, they didn't describe exactly how hot the air is on top of OCU Tulsa. They have how hot the air is in Tulsa. But in order to describe exactly the initial condition, they have to go very, very fine so that when they launch the model, the simulation keep going for 10 days correctly. Right? So that's how sensitive the equation is to the initial condition. Let me finish by this slide. So here is the K epsilon equation again, one more model, and you can see in its all majestic power, look how complicated the epsilon equation is. Okay, so here's a K equation and epsilon equation. Right? And by the way, if some people don't do the K epsilon equation, if you open Fluent or the software that your company is using, you will find one equation model, two equation model. The two equation model to simulate turbulence is the K epsilon. The one equation model is basically saying, come on, I'm not gonna do an equation for this. I know what this guy is. I can model this guy. Epsilon is probably K over some kind of a time because it's the rate of decay of K. I'm gonna come up with a time scale out of L and U. It's L over U. That's how I'm going to get my time. What is the length scale? Well, I will figure a length scale for turbulent. I will figure a velocity scale for turbulent, and I'm done. I don't need an equation for epsilon. Okay?